you very much, Joseph. Thank the organizer for this nice invitation, and thank you everyone that you came here to listen to us. So, I'm going to talk after, I guess it was an excellent talk of Elsa. So the question is, are we approaching a revolution in physics? And the answer is yes. So I could end my talk here, but I will tell you why is that. So, what we have to have in mind is that astrophysics and cosmology have become a precision science. We are living in the century of astrophysics and cosmology in the same way that the 20th century was the century of particle physics. Why? Because technology has advanced in an amazing level that we have a huge amount of data. I will show you the research, the progress of the research. And actually, you have to have in mind that the history of science is a history of tensions between theoretical predictions and the new data. So we have theories to explain the world, we make predictions, and then we compare it with the data, but at some point technology gives you more accurate data that you have to modify your theories, and you have to find new physics and new scientific paradigm. This goes on, and we believe that we are living in this era today. Let me start by some basic principles. First, Thales was the first guy that discovered the term physics from nature, and he was the first guy. It was amazing, the 6th century BC, that we need to investigate nature without superstition, myth, or religion, but only based on observations, experimentation, and superposition and induction, so logical thinking. Right? So we have to have this in mind. Secondly, Pythagoras. The book of nature is written in the mathematical language. So if we want to do physics and explain the world, we need to use mathematics. Again, he discovered the term mathematics, which means literally what is to be learned. And by the way, since in this construction we have a gender balance policy, so we treat equally men and women, so this is Themistocles. According to Pythagoras, he was the teacher of Pythagoras, and Pythagoras says that all that I have learned is due to Themistocles. Now the problem is that everyone in the world knows Pythagoras, but no one knows Themistocles. So we need to point out the important contribution of women in the history of science. So let me continue, then we come to Euclid, which put forward the concept of proof. So whatever we say, we need to prove it, right? So these are the cornerstones of science. Now, let me go back to where everything started. So the first astronomical and cosmological model was the Aristototelian-Ptolemaic model of the 3rd century BC, and of course you have the contributions of many other Greek scientists like Autolycus, Empedocles, Apollonius, Archimedes, Oceanus, and of course Ptolemy. Now, according to this model, the Earth is the center of the universe, and we have all the planets rotating around it. All these are made by 4 elements: earth, water, fire, and air. And the space itself, so the heavens, are made by the 5th element, quintessence in Latin. Okay? Now, this model was so successfully describing observation, which became the scientific model for 1,500 years. It's the most long-lived scientific model in history. Now, in the Middle Ages, we had observations, mainly in Morocco observatory by Persian and Arab scholars, but also in India and in China, that started putting into doubt the details of the Aristotelian-Ptolemaic model. So you see, advanced technology brought new data that put our theory into doubt. What is important, especially here for you important to know, is that in the Middle Ages, people started navigating the planet. So they had also data. They were looking at the stars, and they knew already that the Earth is round. Because if you go southwards, you see that the stars are moving in a lower place in the sky. So this was a non-scientific knowledge accumulated on top of the other things. And we come to Galileo. So in the 1600s, he was the first guy to start making gravitational experiments. Aristotle believed that heavier bodies move faster. So he was the first guy after 1,500 years to test that. And of course, he found that bodies fare with the same speed independently of their mass. At the same time, Bach and Kepler spent 30 years of their life to discover the motion of planets, and now the data were so accumulated that you need to abandon Aristototelian-Ptolemaic model. And we established heliocentric and elliptical orbits. Then we are coming to Newton, when he put together observations of Bach and Kepler and experiments of Galileo, and he gave us the Newtonian theory of gravity. So for the first time, we understood that it's the same force that makes apples falling on Earth and the same force that makes the planets rotating the sun, the force of gravity. And additionally, it's the first time that we understood that in order to understand the laws of stars, so in order to do astronomy, we need to have a theory of gravity. And this is the Newtonian theory of gravity. Now, this was a successful theory. We will make extremely good predictions. However, the advance of technology in the 19th century brought us more precise data. And in 1859, we saw that the Mercury's motion was not in agreement with the predictions of Newtonian theory of gravity. We have these anomalies in the Mercury's motion. Right? And similarly, in 1887, we tried, Michelson and Morley tried to measure the speed of light. And you know, if I have light, so this laser here, if I'm walking, then light should be propagate faster, while if I'm walking the other way, it should propagate slower. But this was not the case. They found that the speed of light was constant independently of the motion. So you see, we have new data that putting our theory into trouble. And then we're coming to Einstein and the theory of relativity. So Einstein thought about all this new data, and he put forward this theory that Elsa talked to you before. And according to this theory, gravity is nothing less than the space-time curvature. So in this theory, matter tells space-time how to curve, and the curved space-time tells matter how to move. Right? Now, I know that this is weird, but a first take-back-home lesson is that this is not just a theory, it has been proven many times. Take two clocks, atomic clocks, put one here, one in an airplane, it goes around Portugal, and when it comes back, it will show different time. These are measured. Of course, it's 1 billionth of the second, the difference, but we can measure it. And also the space-time curvature, for instance, when you are using your GPS in your phone, this takes into account the space-time curvature. So light bends inside out. So this is true, it's not just theories. Now, this is a history of observations of our century. So we are living in the solar system, these are the planets. Our sun is just one star. You see, there are other stars that are much bigger than the sun is this one. The stars form clusters, and we have the galaxy, that you can see it in a very beautiful summer day. And if you start zooming out, then these galaxies form clusters of galaxies and clusters of galaxies, and at large scale, the universe, as Elsa said, is homogeneous and isotropic. So it's the same everywhere. So we are living in a random planet, in a random solar system, in a random galaxy, in this whole universe. We are not the center of the universe, although some people believe that they are. So, these are the observations, and of course, this universe expands, as Elsa explained. It's amazing, but it expands, and this was discovered by Hubble, which, by the way, was the best basketball player of the University of Chicago team. And since it expands, if you go backwards in time, you find that around 14 billion years ago, all the material of the universe that we see was in a super dense and super hot point. And we have this Big Bang, and after that the universe expands and cools down. Okay? Now, as Elsa described, of course, due to the physics of the early universe and the nuclear reactions there, we had a huge amount of photons that after 380,000 years after the Big Bang, they propagate freely. So the prediction is that if you look at the sky at any direction, you could see these photons. This is the echo of the Big Bang, and in this is the case. These people, Penzias and Wilson, in the 1965, they discovered it completely randomly. They were trying to measure something else, but they found this echo of the Big Bang, the cosmic microwave background radiation. Now, two important things that we learned the last 20 years. The first is dark energy, this cosmological constant, so the universe expands faster than expected. And the second thing is the existence of dark matter. So there is much more matter out there than the matter that we can see. Okay? So these are the new observations, and this is now the distribution, so the map of the sky, the distribution of this dark matter. So we need to explain this. Now, what is new in our century? Cosmology in the 21st century, first of all, telescopes on Earth. We have much larger and many more telescopes all around the planet. And of course, this is a difference. We have a huge amount of space telescopes. We are now able to send our telescopes in space. Why this is important? Because you don't have the filter of the atmosphere, right? So you can see much farther and much older. So, what do these new observations tell us? And this is something that our community tries to solve exactly these days, and that's why we have this meeting here. First, what we call, this is a funny name, H-naught tension, actually means that the universe expands faster even what we expected according to this Lambda-CDM cosmology. So today, the rate of expansion is larger than we expected. This is a problem. Now the second thing, it also has this funny name as a tension, concerning the clustering. So clustering is this clustering and this distribution of the galaxies. So all these points here are thousands of galaxies, right? So we need to explain why we have galaxies here and there and no galaxies here and here. And we have theories for that. The problem is that the amount of clustering that we measure is less than expected. Okay? This is what the data are telling us. Now, probably you know that the James Webb Telescope gives some very nice pictures. By the way, according to the expanding universe, if you look further away, it means that you are looking in the past, right? Because light travels more time to come to you. So according to James Webb Telescope pictures, there are too many galaxies too early. And this is a problem that we need to understand, how these galaxies were formed so early. And we have a number of other tensions, I would say, so problems, so disagreements between theories and data. For instance, this cosmic microwave background that we measure, it has a structure. So this is the map of the sky. So red and blue spots are a little bit warmer and a little bit colder, right? However, there seems to be some irregularities here. So this is again a problem. And another possible problem is the gravitational lensing anomaly. By the way, according to general relativity, light bends when it goes around a very massive body. Okay? So this means that we have lensing, we have mirror effects. So if we have a star here or a galaxy, and here is Earth, then if we have a heavy body here, a galaxy, so light can come that way. So if you look up here, you see that the star is here, or the light can come that way. So if you are on Earth, you can see the same star in another direction. So this is a real picture, and you can see things like that. So this is one object, but it has been lensed, right? However, the amount of lensing that we observe probably is different than the one we expect. So this is the question, and this is what I want to get you back home. This is the knowledge of physics that we have. As we say, these are the particles that we have found in CERN and other accelerators. So the quarks, these 6 quarks, U, D, C, the charm quark, the strange quark, top, bottom. We have the electron, the muon, and the tau, and the 3 neutrinos. And we know that the interactions are modified by these gauge bosons. And this model was completed by the discovery of the Higgs boson, the Higgs particle. So these are the 3 out of 4 fundamental interactions: electromagnetism, weak nuclear forces, and strong nuclear force. And this is gravity, general relativity. So this is all we know. This is physics today. And these are the observations that I show you. And the question is, can we explain them, or we need new physics? And the answer is that yes, we need new physics. We need to describe dark matter, we need to describe dark energy, and on top of that, we need to solve all these tensions between theoretical predictions and the data. So you see, again, we're repeating this pattern that we had in history. We have theories, we make predictions, we describe the universe, but at some point we have new data, more precise data, that our theories cannot explain, and we need to build new theories. And we are living in these interesting times recently, so that's why I will call this the crisis in cosmology. Now, what should we do? Okay, we have 2 ways. Either there are more particles than we thought, or the gravitational theory is different. Now, if you follow the first way, apart from these particles that we know very well in CERN and the accelerators, there are other particles, for instance, the quintessence. Remember, in some sense, this is Aristotle's reverse, because we believe that there is a particle all around the universe that makes this job, or other kind of particles. So this is one way. Or you can change the gravitational theory. You see, 100 years ago, 120 years ago, physicists tried to explain the anomalies in the Mercury's motion. The majority of physicists said that, look, this is due to an extra planet between the Sun and Mercury called the Vulcan, and this extra planet causes these anomalies. But Einstein said, no, there is no extra planet. It's the law of gravity that needs to be changed. So, in a sense, we are living in the same situation. Some people say that there are extra particles. Some other people say, no, we need to change the gravitational theory itself. Go to the fundamental theories, string theory, or whatever, that it will give us the new information. And let me finish with the observational revolution that happened 7 years ago, which is the discovery of gravitational waves. Now, gravitational waves are waves of space-time itself. So they're propagating around the universe, and of course, they are everywhere, but especially if you have heavy objects. Now, the most heavy objects that we know are black holes. By the way, black holes exist. We can detect them, and actually, the universe is full of black holes. So if you have 2 black holes rotating around each other, they merge, and then you have the creation of a gravitational wave. And how do we measure that? We have interferometers. So we have 2 in the States, in Louisiana and Washington, and 1 in Italy. So you have a laser, this is 4 kilometers long. So you have a laser going back and forth inside here. When the gravitational wave passes through Earth, the Earth shakes like a gel, and then the laser picture changes. So we know that the gravitational wave passes through the Earth. And just to show you how capable we are, the increase in the length, so this is 4 kilometers, the increase in the length is 10 to the minus 18 meters. 1 billion of a billion of meters. So this is less than the core of the atom, the nucleus of the atom, but we can measure that. And of course, we could say that, how do we know that it was a gravitational wave? If a guy here put his phone on the table, it could call this a distraction, yes. But if you see the same pattern in Louisiana, in Mexico, in Italy, it was not noise, it was a gravitational wave. So you can see this is the signal. So the gravitational wave was emitted in half a second, and we have two solar masses, two black holes of big solar masses, 36 and 29, and the result black hole has 62 solar masses. We count the mass of black holes according to the mass of the sun, because these are completely heavy. So, what can you see here? The sun was 65 solar masses before and 62 solar masses after. So 3 solar masses was transformed in half a second to the energy of the gravitational wave. Let me repeat. In half a second, you have the transformation of 3 suns to energy. So the power of this event is 50,000 times more than the power of all stars of the universe. Just to see how violent the effects are the gravitational waves, and of course the whole universe shakes, and we can measure them. Okay, let me show you now the gravitational wave. Things like that were discovered 5 years ago, so we are now able to see the gravitational wave effect. Now there's no sound there, right? Anyway, the gravitational wave effect from the merger of 2 neutron stars and the gamma rays that are created. Because if you have 2 neutron stars, you have simultaneously the gravitational wave and the gamma rays. So you can independently detect gravitational waves and gamma rays. What can we do in the future to examine whether we are close to revolution? We have to observe, amongst others, the gravitational wave. This is the first tool. For the first time, we can measure something else apart from photons. Right? And what we're planning in the European Space Agency is to send this LISA in space. So this will be 3 satellites with a distance of 2.5 million kilometers away. This will be rotating around the sun. And you are going to have laser going around here. And from this laser, you can detect and study gravitational waves. And from the detection of gravitational waves, you are going to examine your theories and see whether we need new physics. So let me finish here that as humanity, we are doing 5,000 years of observations. By the way, this is the Antikythera mechanism. This is the first computer. It could predict all kinds of planetary motions and eclipses. We have this in the Archaeological Museum of Athens. This is around 1 century BC. So we're doing 5,000 years of observations and 500 years of organized observations. From the first time that Galileo decided to look at the sky with his telescope. Okay? Now, imagine how the picture of the universe changed after 400 years of electromagnetic observation. What people believe in the 1600s and how we know that the universe is today. We are doing gravitational wave observations for 8 years. So you can only imagine what the picture of the universe will be after 400 years of gravitational wave observation. So, yes, we are approaching a revolution in physics. Whether we are close or far, we don't know. But for sure, according to the pattern, we are living in these interesting eras, and the journey continues. So, thank you.
Thank you a lot, Emmanuel, for this very, very nice talk. I'm sure there will be questions for Emmanuel.
So everything was clear, eh? Yes, please.
Already measured
The radiation, yeah.
for much earlier. I don't recall why it was sort of forgotten, and the Ptolemaic theory was so powerful.
Very good. Good. Okay. So this has to do with epistemology and the history of science, because in many eras in history, you have good ideas that are correct, but people neglect them. Why? Because they don't feel the general philosophical and sociological paradigm that exists. Not only that, I mean, Seleucus of Seleucia believed that Earth is moving, and some other people, but this was neglected because the paradigm was this Aristototelian-Ptolemaic model. Yeah, it's quite strange, but it happens many more times. I mean, even Copernicus, he was forgotten for many decades, and even in our century. I mean. So this goes on and on. It's a more general thing, how ideas spread. Good question.
Other question? I might have one. Allow me to speak.
Okay, so you thought that universe is homogeneous. From that, I should understand that it doesn't. I mean, if I move to the different places in the universe, I will see the same thing, right?
Yeah, but okay, this is a conjecture because, as you say, we cannot move to different places of the universe. But yes, this is the idea.
Almost the same.
Yes.
Right?
Mm-hmm.
But why it is different in time? You told me. I mean, nothing spatial in space, right? I mean, there can be there, the same universe. But why at a very spatial point in time?
Very good. So your question is why we have the arrow of time, and actually we don't know the answer, and it is related, of course, with entropy and the second law of thermodynamics. But strictly speaking, I mean, we don't know why we have this, right? But it is what it is, so we need to explain that. So there are many theories that, okay, at the macrophysical level, there is no, time arrow, but it arises when the complexity of the whole system arises. So it's an open question, why we have that. And actually, it's an open question why we humans can move in space wherever we want, but not in time. I mean, we are confined in time. We are, 80, 100 years, that's it. So yes, these are open questions. Yeah.
It shouldn't be true. Maybe when we look further with our telescope, it is not because we are looking, the universe was different in the past. Maybe the universe is not homogeneous. When we go far away from here, the universe is different. Not because of time. But the universe may not be changing in time. So, where do we know that this is wrong?
Yeah, we don't know that. That's why we're doing observations. In principle, this could be. So you see, this is the idea that we're making observations and we build our theories, and at some point, the bricks do not hold. So you need to change your theory. And relativity is a very radical change of thinking, that there is no absolute time and absolute space. So yes, probably in the future, we're going to have also revolutionary changes. Yeah, or not. I don't know,
What dominates you?
Yeah.
Time will become homogeneous as well.
Questions?
I would like to say that I feel like what's the biggest limit for the time is that we cannot travel into the past.
What do you mean?
Is that we cannot travel into the past because we need to reverse the arrow of time, because otherwise I wouldn't call it a limit in time, in the sense that if you take the human lifespan and you multiply it by the speed of light, that is much farther than humans have ever reached in space. We only went to the moon.
Mm-hmm.
And at the same time, we know by special relativity that, at least in theory, we can move as much to the future as we want if we have machines that travel fast enough while using our normal lifespan, in some sense.
Yeah. The first part of the question, there is a deep concept called causality. You cannot violate that. You cannot go in the past and kill your grandfather because then you wouldn't exist to do that. So this was a conjecture by Hawking called cosmic censorship. So you cannot have things like that. However, in the future, if you're moving very fast, you can do that. So when you come back, here, you will be thousands of years in the future. But causality, you cannot violate it.
Can you create particles in matter?
To create what?
Matter.
Out of nowhere? I don't know. Well, this is an interesting question. I mean, probably nobody knows. And by the way, you know, I mean, when we're doing physics, this is why I mentioned we need to use mathematics. So, according to our theories, we cannot go back to zero. We can explain things after 10 to the minus 44 seconds after the Big Bang. So, you cannot ask what happened before that because we don't know how to explain it. Either the universe was created or it's an infinite universe and this Big Bang is just a bang in our observable part. We don't know. So in Weinberg, which was the best physicist of the second half of the 10th century, in his famous book, The First 3 Minutes, he doesn't mention the word Big Bang. He just describes things from the point he can use mathematics and on. What happened before that, we don't know. It's philosophy there. Either it created from nothing or it exists forever. I mean, we don't know that. So in your answer, probably yes or probably no, whether a particle can arise from vacuum.
In that sense, I have a question.
Good.
Is it possible that time is discrete?
Good. Very, very good. Now, what is time? We have many theories. So what happened at the microphysical level, we don't know. There are theories. For instance, according to quantum gravity, it could be discrete. This is a space-time form. Or it will be continuous. We don't know. For the moment, we have theories up to from a level and up. Now, what's going on at the macrophysical level? Perhaps there are theories that time does not exist at the fundamental level. It arises statistically, so only space exists. This is what we're doing in a theory called low quantum gravity. So you see, all these are possible, and this is what we're doing as a community. We try to understand what's going on with these concepts.
But what about Planck time?
Good. Planck time, or Planck length, or Planck energy are the limits of our description of gravity. Because in smaller times or smaller space on larger energies, we need to have a theory of quantum gravity that we don't know anything about that. So we are doing physics after that. What's going on in less times or less levels, we don't know.
And I have another question. So what happened to the missing solar, the 3 solar masses after the black hole? Was it just
The energy of the gravitational wave.
but also some radiation, right?
Sure. I mean, you have gravitational radiation. Now, in neutron stars, you have also electromagnetic radiation. So, exactly. The gravitational wave is gravitational radiation.
Yeah, so the conversation is getting very nice, very interesting. Right? So, time travel is a headache, okay? And not just the causation of causality, but also the production of matter and also information, okay? So, there's different types of paradoxes, okay? One of them is the Emmanuel paradox, which you mentioned. That one, I mean, it's strange, okay? Because like you mentioned, when you go back to the past and you know that automatically your grandfather, but you're there, you know?
Yeah.
That's a violation of causality. But there's another paradox, which not, I mean, it's not very well mentioned. It's the information, I mean, it's the production of information, okay? It's the so-called closed loops, okay? The causal loops. So while you're alone, and you get this very strange knock on the door, and you open the door, and there's an old man, you know, he's very familiar, okay? And he gives you a book, okay? So you thank you very much, and then when you close the door, and you put your book away. Several years later, I mean, you go back to the book, and it's a book of quantum gravity, okay? Quantum gravity is there. Okay, all already written out. Okay, so you publish it, you can be famous, you win a Nobel Prize, you know, and then years later you're very old, and there's a kind of a small paintings, you know, which tells you that theory, you know, can make a machine, a time machine. Okay, so what you do is you make a time machine, and you take that book back to your past and give it, well, to yourself. There's no violation of causality here. But there's a production of information. Where did this information come from?
Good. Very good point, Francisco. But just, yeah, I totally agree. But even, I mean, according to many physicists, we have not understood what is information. We don't have a definition of information. We cannot put into equations. You see, it's interesting as some Nobel Prizes to say that, 250 years ago, people were using transformations of energy, so Watt and the others transformed energy from the thermal energy to kinetic energy, but they didn't understand what is energy. So we understood what is energy 100 years later, and you see the difference. I mean, people who were using energy, they were measuring the energy in, sacks of coal, but they didn't know what is energy. We understood it 100 years later. So many people say that with information, we are in the same situation. We are using it, but we don't have any idea what is it. And you see, measuring information in kilobytes and megabytes is like measuring energy in coal in sacks of coal. So I totally agree with you, up to the point that, seriously, we don't know what is information. So the information paradox is very, very important, and it's related with all this black hole thermodynamics and everything. But okay, let's do one step at a time. I mean,
You don't know what information is, but you know what disinformation is.
good. Good.
Okay, I just have this one small question. Are you really sure that black holes exist? Because there are many candidates and many alternative massive objects that can mimic black hole shadows, and in that sense, we don't know in fact that if black holes exist.
Okay, good question. Now, black holes, not the ones that we predict, black holes in general exist, because we know these supermassive black holes at the center of galaxies and all this stuff. Now, what are the details of that? I agree with you that we don't know, because this will have quantum corrections and everything. Perhaps there are no singularities, etc. But the general concept of a black hole exists, of course, and there are too many.
We have images.
Yes. No, this is where I'm saying that there is something there. Now, whether this is the Schwarzschild black hole or the quantum gravity corrected Schwarzschild black hole, we don't know, but it exists something called black hole.
It exists.
Yeah. No, yeah.
We might have a question for you, because you have been quite convincing about the fact that we are approaching the revolution of physics.
Yeah.
At least to me, okay? But there is a general idea in modern cosmology, which is the fact that links structures as we observe today to intimate processes which are random at the beginning of the universe.
Mm-hmm.
So in this sense, we might think that all the particles in the universe are just falling and just deviating their straight path towards structures which basically have their origin in the randomness.
Mm-hmm.
Isn't it reminding a bit the old idea of Epicurus physics?
Yeah. I mean, okay, first of all, we're talking about the observable part of the universe. And yes, the initial conditions were completely chaotic and random. And at least in our observable part, we have this evolution. In other parts outside the horizon, perhaps the evolution is completely different. But yes, our observable universe is a result of these quantum fluctuations of these primordial fields. So in some sense, you are correct that we arose from chaos.
Yeah.
Good.
Let's just other questions?
So you're saying that we're approaching evolution in physics, right? But doesn't it sounds more like that we need the evolution in physics, right? Sounds similar, but it's not, in the sense of like, consider for example like LHC, they found a Higgs boson, standard model is well verified, and now they're stuck. Mm-hmm. So to an extent, like, are we getting so many data from cosmology and astrophysics and new flows that we are generally thinking that something will come out of them, or we just hope that something will come out of them because we don't have an answer to some of these problems?
Good question. Yes, we are collecting a huge amount of data because technology gives us this ability. Now, in CERN, they went through this limit because in order to get new data, you have to go to higher energy, so you need to spend billions and billions of euros to enlarge CERN. But in cosmology, it's much cheaper. You don't have a limit. I mean, particles are coming with huge energy from the universe. So our laboratory is the whole universe. All we need to do is to observe it. So we are optimists that we have a huge amount of data that will lead to the revolution in physics, for sure. Like we did, look at the time scale. How the picture that we have for astronomy was more changed in the last century. So from Hubble to today, obviously we're not going to stuck here forever. We have new data, and sooner or later we will have new ideas. I mean, even the idea of the accelerating universe, which is a kind of revolution, came around 25 years ago, which is nothing. So from today to 2050, it's for sure that we're going to have breakthroughs. Remember that we discussed this today, when you will see that in the news.
Okay, final questions, final comments, final thank for the moment.
I have a
Please.
question.
Yes.
The question is not about the revolution itself, but about the nature of the term revolution, maybe.
Oh, there?
The term revolution.
well.
When we think about the revolution in physics, we usually think about the transformation from Aristotelian to Newtonian physics, and then from Newtonian physics to relativity and to quantum mechanics. So whole theories that were not exactly thrown away because everything that Newtonian physics explained we need to continue to explain to reduce the Newtonian physics in those cases, but they were replaced by new theories. And on the other hand, what we had throughout the 20th century was like amazing advancements, which produced many new theories, which were incorporated in a bit of the same framework of general relativity and quantum mechanics. So I wonder if, I've heard some people say that in terms of the underlying, let's say, theoretical basis, we've already reached the end, but even though we can, in terms of the things we put in those theories, like I don't know if I can...
May I make a comment on that?
Yes.
I think it was Kelvin that said in the late 19th century that the role of physics now is just to improve the precision of measurements and right?
Yes.
So, I mean, there's tension is the key word of this conference. Something will give, and I think that in the next, hopefully not so many years, there will be some sort of theoretical approach that makes sense of the of the data we can explain. Because that's basically how things move forward. If we take more the paradigm shift, right?
That's why observations is important, because it's observations which drive these conclusions, okay? And the theory in quantum element will explain that the observation, quantum mechanics is based on observation, observations that drive these conclusions.
Or maybe this is in steps. There's some theory that is able to explain quantum mechanics and gravitation, and then something else for information. One of both. Maybe there's still some stepping stones until some form of unification. Seems plausible to me.
One times mentioned about the gravitational waves, right?
Yeah.
So who knows? We usually stage that we point our gravitational telescope to the sky, like Galileo, he was looking at with his telescope, right? So what sort of new discoveries await us, through gravitational waves, we know about black holes, about lasers, what new discoveries will we have, these will be something interested in exploring the universe, so it's very fascinating times to be living, right?
Perfect, yeah. And just a comment, do you know the word revolution that we're using for revolutions? Do you know where it comes from? What does it evolve means, revolution? In Latin. It's the rotation of the planets. This word discovered by Copernicus, and it was, so the idea was so revolutionary that the term revolution, meaning the revolution that in Latin languages, we call revolution the revolution. So it comes from astronomy, that word. Google that and you will see the story of Wikipedia. So scientific revolutions were so strong that gave the word revolution. So yes, we believe this is how science moves. I mean, we are going to find new things. This is not the end of history. There is no end of history, right? We are going to go further and deeper and increase our knowledge to a more and more fundamental level. Now, whether nature is simple or not, again, this is something that we have inherited from Pythagoras, that nature is not, it's simple. We don't know. Perhaps it's simple, perhaps it's not. That's why we're scientists, to investigate it, and in the end of the day, we are going to gain deeper and deeper knowledge.
Okay, if there are no more questions, I would like to thank Emmanuel.